Sir Isaac Newton and Godfrey independently developed calculus in 17th century, which provide a framework of solving differential equations. Newton used calculus to solve problems in physics and astronomy. Mathematicians such as Euler, Abel, and Cauchy made contributions to the study of ODE. Differential equations are classified into two groups, which are ordinary differential equations and partial differential equations. We'll be focusing on ODE in this video. An ODE is a mathematical equation that describes the relationship between a function and its derivative, where the derivatives are taken with respect to a single independent variable. This is the general form of an ODE, where y is the dependent variable, x is the independent variable, and fxy is a function of x and y. The equation describes the relationship between the derivative of y with respect to x and the value of x and y themselves. ODE can be further classified in terms of order, linearity, and homogeneity. For example, first, second, and higher order, linear and non-linear, homogeneous and non-homogeneous, and these are the examples. These terms can be combined together to form different types of ODEs, which are solved using different methods. As for first order, separation method is used when the dependent and independent variables are separable. Introducing y equal to uv, where the ODE is non-separable but homogeneous linear. Exact method is used when the ODE is in this form and the partial m over partial y is equal to partial n over partial x. If not, factor f must be introduced. Integrating factor is used when to solve non-homogeneous linear ODE. Bernoulli's equation is used when the ODE is non-linear and non-homogeneous. The method of elimination is when the ODEs involve two or more equations that contain derivative of two or more dependent variables. And lastly, the Laplace transform. For second order ODE, constant coefficient is used when we have second order homogeneous linear ODE. The method of undetermined coefficient is used when the ODE is in second order non-homogeneous linear. Then, method of elimination, Laplace transform, and Fourier series are used to solve second order ODE as well. These are the examples of solving ODEs using different methods. Please take a pause to read. Solving an ODE means finding a function that satisfies the equations. In the example below, after it is solved, the final equation has mathematically described the relationship between y and x. ODEs are also applied in material science. Firstly is the grain growth equations, which can be modeled as dd over dt equal to k over d. It is used to model the change of grain size of material over time. Grain size of a metal can have a significant impact on its mechanical properties. From this table, we can observe that the smaller the grain size, the higher the yield strength and the tensile strength, but decrease in ductility. The graph also shows that the smaller the grain size, the greater the gradient, where the gradient is represented by Young's modulus of elasticity. Separation method is used to solve the grain growth ODE, where we separate the k and the d term and solve for the integrals. After the boundary condition is substituted, we get the particular solution of d squared minus d naught squared equal to kt. And this is the example of solving the grain size d after an interval of time using the modeled equations. Second application is Euler-Bernoulli's beam equation. This is a fourth order linear homogeneous ODE, which describes the vertical deflection v of the beam at a position z that is subjected to a transverse dot w. The term d power of 4v over dz power of 4 represents the curvature of the beam. E is the Young's modulus and I is the moment of the beam. This equation is commonly used in analysis and modeling the beam deflection under transverse load, ensuring structural safety and understanding the material's property. To solve this ODE, 4 times integration is done. EIV'' stands for the shear force, negative EIV'' stands for the bending moment, V' is the angle of deflection, and lastly, V is the vertical deflection of the beam. By solving the boundary condition, we can get the particular solution, which describes the vertical deflection and the angle of deflection of the beam under a transverse load. This is the example of solving vertical deflection and angle of deflection. When the condition is given, by substituting the values into the derived equations, we can get the vertical deflection of 38.2 cm and angle of deflection of 0.00121 radians under 2000 Newton per meter load.